So the question's asking us to rank the labeled hydrogens from most acidic to least acidic. So it has an NH, a CH, and an OH. So what's in common? They all have hydrogen, right? What's the differences? Nitrogen, carbon, oxygen. What's their relationship to each other on the periodic table? Electronegativity, right? They're in the same row. Right? They're in the same row. It goes nitrogen, or carbon, nitrogen, oxygen, fluorine in the periodic table. So electronegativity is increasing as you go from left to right in a row. So that'd be a more polar bond, the more electronegative the element is. So the most acidic one would be 2. Then it would be 1. Then it would be 3. It's just based on the polarity of the bonds. Okay, so this is a question, I think it's question number 3 from the 2017 exam. Version A. So fill it on the lone pairs, formal charges. So I got the lone pairs on the first side, formal charges. Oxygen with 1 bond and a full octet has a negative charge. Nitrogen with 4 bonds and a full octet has a formal plus charge. So I've balanced my charges, that's all good. Curved arrows. So what new bond did I make? Did I make an NH bond? A sigma N to C, right? Right, so we're making a sigma bond between nitrogen and carbon. All right. What bonds are we breaking?
No, that's double bond, or the pi bond on the oxygen and carbon.
Right, the pi bond between carbon and oxygen, not the double bond, the pi bond. Right, so we need to show arrows to show that happening. So who's going to lose electrons here? Where are we going to start our arrows at? The nitrogen, right? That's going to react with that carbon to form that sigma bond. But you see the nitrogen has a plus charge over here, so it must have lost electrons. That's where that's the flow of electrons had to start. We need to show electrons also, that pi bond breaking, so 2 electrons going to that oxygen. Do you see that? Right, how the flow of electrons. So we knew we needed to make a sigma nitrogen carbon bond, so we had to start our arrow at that nitrogen, that lone pair the lone pairs of electron density, which also means this nitrogen, specifically that nitrogen, is what? The nucleophile. What's my electrophile then? Oxygen. Not the oxygen, the carbon. Right? The carbon. Right? The carbon's the electrophile. The carbon's electron deficient. The carbon's the one that accepts the electrons. Right? The nitrogen's the nucleophile that donates the electrons. So let's say we have this chair, and the question says, what atoms are going to interact with this bromine in a 1,3 diaxial interaction? So right now the bromine's in what position? Equatorial. So to figure out what's going to interact with in a diaxial interaction, we need to do what? We need to do the ring flip. Right? So we need to do the flip. So the bromine was equatorial in what position? Up or down?
Up, down.
Down. So now it's going to be down, of course, and axial. What else is axial with that bromine? So there's an H here that's axial. There's an H here. Right? So what else is axial on the same side as this bromine? That's going to be in a diaxial interaction. So it has to also be, since the bromine was down, it has to be on the bottom face as well. So it'd be these 2 hydrogens are the ones that will have diaxial interactions with the bromine. They're on the same face, and they're axial when the bromine's axial. That's all. That's a good way to look at it. So why is it 1,3? The 1,3 just refers to, if you look at this bromine, 1, 2, 3 carbons away, that's where the other axial position's at. So it's 1,3 because it's just 3 carbons away. That's all that 1,3 matters. Either way you go. 2017 exam, version A, Number 12, the question asks, given this chair and the circled fluorine, what is cis to it? What are all things that are cis to the fluorine? So he basically is asking, do you recognize that this fluorine's on the top face, or the up is up? What else is up? Now, is it being up, you can be equatorial and up and axial and up, right? That's kind of what I'm asking here. So if you go to each atom, right, on the same face, at this carbon, what is up? This one. Hydrogen's up, right? The next one? Bromine. Next one?
CH3 equatorial.
Yep. Next one?
Hydrogen axial.
Yep. Next one?
Chlorine equatorial.
Yep. Easy as that. That's all I'm asking you to see is to see what else is cis to that fluorine, what's on the same side. Yeah. Don't overthink it. That was all. So just looking at reaction definitions, this is number 5. So how do you know this is a substitution? Really simple. There are H's all over this ring. And in the product, what happened? You replaced one of these H's with a bromine. Replace or substituted. So it's a substitution. That easy. Anything that gets substituted, that's a substitution reaction. Replace an H for a bromine. Substitution. You could have something like this. What kind of reaction is that? The substitution? No. What have I done? Elimination, right? Make sure you draw those hydrogens in. I just took off, right? The hydrogen eliminated, made a pi bond. See a pi bond being made? That's an elimination. So substitution, elimination.
Would a pi bond always be made in elimination?
Pi bond's always made in elimination. Always, always, always. So the opposite of elimination is addition. So you take the same thing. If you get this, what kind of reaction is this? That's an addition. You added two things across a pi bond, right? Adding things across a pi bond is an addition. And last one is just a rearrangement, and that could be, one example was from that to that. So a E-alkene, right, where the hydrogens are on opposite sides, or the highest ranked priority groups are on opposite sides, to a Z-alkene, where the hydrogen on the same side, Z same side. This would be a rearrangement. We didn't add anything. We didn't substitute anything. We didn't eliminate anything. We just moved atoms around in space, or we just moved the bonds around. We didn't actually, change the molecular formula. That's just a rearrangement. So number 10, trying to explain why this CH bond is not acidic using words and pictures. So another word of warning, I do not want full paragraphs writing out diatribes. I want short pictures to show me here. So first thing you probably look here is this is an sp3 hybridized carbon. So sp3 hybridized. That means it has sp3 hybrid orbitals. And that if this reacted, I would have this molecule, which means I'd have a lone pair in an sp3 hybrid orbital. sp3 hybrid orbitals are far from the positive protons in the nucleus, making it less stable and less likely to form. Boom. Perfect answer. Draw a molecular orbital. Show that you understand the size and shape of it. Know that it's going to be far from the nucleus. Of course, what's in the nucleus, positively charged. Like, so why is it less stable as far from the nucleus? You got to say something about the positively charged protons. You can't just say it's just because it's far from the nucleus, but why? Because there's positively charged protons, opposites attract. You can throw that in there too. So that makes it less stable. Something's less stable. It means it's less likely to form. Right? So that means this acidity of this molecule, or that CH bond, is not very high. So let's look at possible resonance forms. So the first thing I would do here is I would number the atoms that possibly are part of resonance. 1, 2, 3, 4, 5, 6, 7. Notice I didn't number this last carbon. This carbon can't be part of resonance. Why can't it not be part of resonance? What's the hybridization state of this carbon? It has no pi bonds. No p orbitals. It can't be part of resonance. So don't even bother numbering it. Well, this carbon, can that be part of resonance? Absolutely not. It's sp3 hybridized as well. No, thank you. What's the hybridization state of this oxygen? sp2, right? So that's lone pair being a p orbital, so it can do resonance. Nice. So lots of options here. Let's do the 2 electrons, the oxygen, for a new pi bond between O1 and C2. The pi bond between 2 and 3, both those electrons will go to carbon 3 this time. Resonance arrow. Right, nice thing about resonance, of course, the positions don't change. So you can just fill in all the atoms right away. Balance our charge. Renumber everything. 7, 6, 5, 4, 3, 2, 1. So let's make sure we got everything right here. So we have a new pi bond where? Oxygen in there. And we have a lone pair on 3. So there should be a negative charge on 3 then. And if I have negative charge, I need to have a plus charge. Or should there be a plus charge? On the oxygen. And then I'm missing, right, don't forget, oh, there's still a pi bond between 4 and 5. So there's one resonance form. Want to keep going. Move these electrons for a new pi bond between 3 and 4. Make sure you show up between the 2 atoms. The pi bond between 4 and 5 will break. Those 2 electrons will go to carbon 5. Resonance arrow. Number my carbons. 7, 6, 5, 4, 3, 2, 1. Still a pi bond between 7 and 6. New pi bond between 3 and 4. Lone pair of electrons on carbon 5. So good? Keep going down the line. New pi bond between 6 and 5. Lone pair of electrons go to 7. Resonance arrow. Fill in stuff that hasn't changed. Post charge. Pi bond. Lone pair. Number my carbons. Make sure I didn't lose anything. I've already lost something, I can tell you right now. But it wasn't involved, so I didn't care. There was start out with a methyl group on carbon 4 that just somehow got lost along the way. But now I put it back in. It's all good. There's 3 resonance forms. Which one's the best? If you had to ask which one is the best, so obviously this first thing is probably the best. But after that will be the best. A, B, or C? A, B, or C? What's the best resonance form? Opposites attract. A. The negative and plus charge are as close as possible to each other. This is probably the most likely resonance form, or the best resonance form, because the charges are as close as possible together. All of them have full octets, so that's not a problem. The octet rules works for all of them. So after that, we want opposite charges as close as possible. So that would be A. So a sapling question with a number of things like Lewis asking what is the Lewis acid, what's the Lewis base. Lewis acids, of course, accept a lone pair of electrons. A Lewis base donates. Lewis acids are electrophiles. Lewis bases are nucleophiles. Nucleophiles are electron rich. Lewis acids are electron deficient. So sodium would definitely be a Lewis acid, right? Plus charge. Chlorine, negative charge, would definitely be a Lewis base. Boron, right, doesn't have a full octet, right? So this would be boron with 3 OHs around it. So it only has 6 electrons around it. So it's actually going to be electron deficient. So it's also a Lewis acid. SO3, if you think about the central atom as sulfur, it's going to look like that. That sulfur is going to be pretty electron deficient. So this is also a Lewis acid. And then the one I disagree with, or I'd say water can both donate electrons, but it can also donate a hydrogen. So I think water is really both a Lewis acid and a Lewis base. Sapling, you want just Lewis base.